All right, everybody. This is the last video for chapter 5 on conditional probability. So we're going to talk about some tree diagrams, talk about the last couple of formulas, and that will be that. So here we're looking at this person, and she hits the snooze button on her alarm clock 60% of the school days. If she does not hit the snooze button, there's a 90% chance she makes it on time. However, if she hits the snooze bar, there's a 70% probability that she makes it on time. So the first thing you want to do is make a tree diagram. And so tree diagram, you start with a little starting point, and we have our first little branches. These are kind of just called branches. And here we're looking at the likelihood that she hits the snooze button or not. So I'm just going to label this S and S complement, which is the same thing as not snoozing. And the likelihood she hits snooze is 0.6, so I can just put a 0.6 right here. And down here I can put a 0.4. And if there's 60% chance she snoozes, 40% chance she doesn't snooze. And then from here we can kind of keep breaking these apart. And so then here we can either break this down into on time or on time complement, which is being late. And if she doesn't hit snooze, the likelihood, so if she doesn't hit snooze, the likelihood that she makes it to class on time is 90%, so 0.1, or 0.9, sorry. And then the likelihood that she's late is 0.1. And I can do the same thing here, break these apart. And here we have 0.3 that she's late, and 0.7 here that she's on time. And so the nice thing about tree diagrams is that you can kind of calculate probabilities pretty easily. So you can find the probability of being that she hits snooze and is late, or that and is on time, by just multiplying these two probabilities together. Right, 0.6 times 0.7 will represent the likelihood that she hits snooze and is on time. Okay, you could also do the same thing, snooze and is late, by multiplying those together. And you could do does not snooze and is late by multiplying those together. Right, so the tree diagrams are pretty nice. And so the first question is find the likelihood, or on a randomly chosen day, what's the likelihood that she is late for class? And again, the reason why tree diagrams are nice is because when I start highlighting things, I want to find the likelihood she's late. So I just need to follow these branches. So I'm going to take this branch and this branch, right? She's late in that scenario. And then I've got this branch and this branch. And so when you want to figure these out, all you're going to do is start multiplying across. So you have 0.6 times 0.3 plus 0.4 times 0.1. And this equals 0.22. So the likelihood that she's late is 22%. And then you can answer part C. What's the likelihood that she hits snooze given that she's late? So snooze given late. Well, that's the likelihood that she hits snooze and is late. Snooze intersection late, so both divided by the probability that she's late. Okay, we just found the denominator. We just found the probability that she's late. This is 0.22. And the likelihood that she snoozes and is late is going to be this little red branch here, which would be 0.18. 0.6 times 0.3 is 0.18. You have 0.18 divided by 0.22, and that's 0.818. Okay. And so that leads into this general multiplication rule, which is the probability of A and B. So again, and is multiplication, or is addition. It's equal to the probability of A intersection B. So we just kind of write this as A intersection B. What's in both of them? Which is equal to the probability of A times the probability of B given A. Okay. And this is not on the formula sheet. So there's a formula sheet on Canvas. Make sure you look at that to see what's on there and what's not. So this one is not on there. I can tell you that right now. So now, which is better to use, a tree diagram or a two-way table? You can use either. But when you are given conditionals, it is often easier to use the tree diagram. If you are given counts and proportions, typically easier to use two-way table. So you can use either one. It's up to you. Those are kind of just some suggestions there. Okay, try this one on your own. We'll go over it in class. So there's that. And so that leads to the last page of notes here. So what's the multiplication rule for independent events? Well, if we know that the events are independent, we know that the probability of B given A is just equal to the probability of B, right? Because A had no impact on B. Likewise, the probability of A given B, by the same argument, is just the probability of A. Because B had no impact on A. And so when you want to find this, when you use that equation that we just wrote down, so the probability of A intersection B is equal to the probability of A times the probability of B given A. Well, if they're independent, then you just end up with probability of A times the probability of B. Okay, and that's from this right here. Right? Because we know they're independent, we can just multiply the two probabilities together. So that's why when you're flipping a coin, if you want to find the likelihood of getting a head and a head, you just multiply 0.5 and 0.5 together, because those are independent events. And again, these are not on the formula sheet. Okay, last question. So here we're looking at positive results in a non-invasive test given to the first trimester of pregnancy. And so we want to find the probability of at least one positive. Okay, and this is the same thing as saying 1 minus the probability of no positive. And so the likelihood you get a not a false positive is going to be 1 minus 0.05. That's just from the problem. There's a 5% chance. There's 0.95. Okay. And it's pretty fair to assume that these are independent trials, right? Because I don't think pregnancies are going to be impacted by one another. So we can kind of assume that these are independent. And so when we have 100 women, we can do this 0.95 times 0.95. We're going to start multiplying these probabilities together. We do this 100 times, right? Dot, 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 right? And this is the same thing. When you start multiplying the same number a bunch of times, that's just doing an exponent. So you have 0.95 to the 100th power. Okay, so when you type that into a calculator, you get 0.0059. And so this is the likelihood of having no false positives. So now I can just take this and plug it in right here. And so I get 1 minus this number, which is 0.9949. So when you sample 100 people, there's a 99.41% chance that you're going to get at least one false positive. Okay? And if you think about that, that makes sense, right? Because if we have 5% are false positive, right, what would you expect to have? You'd expect to have 5 people get false positive. So when you have just one false positive, obviously that number is going to be really high, right? And so it's 0.9941. Okay. And I want you to think about this one. Are these independent? Are these not independent? Could you just multiply 0.5 and 0.5 together to get 0.25? So think about that, and we can kind of go over that in class. The last page of these notes is just a little activity. It would have been if we did it in class in school, but if you want to try it on your home, please go ahead and use some popsicle sticks. But we may look at that. But that's it for these videos. That's all of chapter 5, guys. So if you have any questions, again, as always, please let me know. But if not, have a great rest of your day.